don't actually know.
Why is Macaulay bleeding?
Okay, everybody, welcome. Happy Pi Day. Happy, we are right on the cusp of spring break too. Doesn't get any better than that. Oh, but it does get better than that because today we have the incomparable Neil Calkin, who, despite his pleasant demeanor, says no pie for you.
No, no pie. So happy North American happy North American approximation to Pi Day. I think it's only in North America that we have this ridiculous system of Middle Indian dates. I'm going to go on a short rant. Month, then day, then year. It makes absolutely no sense. Year, then month, then day. Yep, I use that for naming my files because that way when I list them alphabetically, they show up in date order. That is 2025.03.14.2025.3.14. That doesn't work. So in celebration of the fact that this is not Pi Day anywhere else in the world, and it shouldn't even be Pi Day here because here's a secret. I'm going to let you in on a little detail. Pi is not 3.14.
No.
I hope you've all seen the meme. Mirror image of 3.14, of course, that's about as close to pi as 3.14 gets. So in honor of it not being Pi Day, I thought I would tell you about some things that are not pi. If anybody is interested, I've got a handful of copies of a paper that appeared a couple of months ago that Liza Gallagher and I wrote. It's called No Pi for You. And it's in the Recreational Mathematics magazine that comes out of Portugal. I'm basically going to go through much of that paper today. So if you want to have any of the details, they're in the thing. So, here's a really surprising result. Some numbers are not equal to pi. Wow. In fact, it's true for most numbers. If you're careful with the probabilities, you can show it's true for almost all numbers under almost every distribution on the reals, or even the integer. But some numbers are presented as pi, and everybody knows we were all taught in school pi is 22/7. Those of us with better teachers were taught pi is roughly equal to 22/7. Some of us with great teachers were taught continued fractions, and that's why pi is close to 22/7 and why the subsequent approximations work nicely. Pi less than or greater than 22/7. Come on, you can do that. You can do this in your head. 22/7 is 3.142. Sorry? 22/7 is greater than pi. So let's prove this. Okay, let's compute pi. We've got good ways of approximating it, and it comes out to 3.1415926. Some years I memorized 20 digits for pi day just so that when the person in the college office says, can we interview somebody about pi? How many digits do you know? I'll say 3 point something. No, seriously, how many digits do you know? And I'll rattle off 20. But they interviewed me 2 weeks ago or more, so this year I didn't have to memorize it for today, so 3.14 something. Sorry, 3.141 something. So we can compute it and show that it's less than 22/7. But wouldn't it be nicer if we could give a more mathematically insightful proof? So fortunately, 1968 Putnam helps out here. Some of you are going to be undergraduates still next year, if we don't let you graduate. Quick ad, there will be a seminar Mondays and Wednesday afternoons, training for the Putnam, if anybody is interested in taking the Putnam, Toby. Hazel took it last year.
I got it too.
Took it last year, we'll take it to, no, this is really good. This is, none of the scores on the Putnam are hard to achieve. And so the fact that 5 of the 6 students who took it last year got positive scores. So, you know, come take the Putnam seminar next semester. Quick ad. Okay. So 1968. Rather simpler question than some. It's an integral. And integrals, when you can do them, well, it is a definite integral, so that's going to make it potentially harder. But it is not a definite integral that's hard to do. We expand it out as rational function plus polynomial, and we'll get something which is easy. And it turns out that when you do the computations, the integral comes out to be 22/7 minus pi. There's an arctan in there. It's got a constant over 1 plus x squared from 0 to 1. So seeing a pi turn up is not surprising. Sorry, I'm still. So why does that show that 22/7 is greater than pi? Well, the integrand is positive on the open interval 0, 1. We're integrating a positive function, the interval 0, 1. This is positive, therefore 22/7 minus pi is positive. So that is my favorite application of a Putnam problem. You could ask, what happens with other approximations to pi?
And I'm asking. No possibility.
So let's take 355 over 113.
Oh, let's see.
Again, an integral from 0 to 1, x to the 8, 1 minus x to the 8. 25 plus 8, 16 x squared over 3.74. 1 plus x squared, the same sort of trick. This is the next continued fraction lower bound for pi. And it's really quite close, but we can again see that it is positive, this difference, because it is equal to this integral. And this integral is one that, I mean, these days we don't do, we send it off to Maple or Sage or Mathematica, and it pops back. the integral. So quite mechanically, we see that this is in fact a lower bound for pi. Sorry, not an upper bound for pi, which is good because it is the continued fractions alternate lower, upper, lower, upper, lower, upper, and this is two continued fractions on from this one, so it better be the same side of pi, just closer. So we shouldn't be too surprised that these things are not pi. They're continued fraction approximates, and since pi has a continued fraction with infinitely many terms in, we shouldn't expect any of the finite terms to be equal to pi. Right? They cannot be equal to pi. From the nature of continued fractions, finite continued fractions are rational, pi is not rational. Well, there's another proof that these are not equal. Right? What is not rational? So that's kind of mundane, but kind of a nice stuff. So my next example of something is pi for a while. So a couple of decades back, John Borway, now late John Borway, good friend of mine and mentor of mine, was computing some things with Maple. He was a big fan of Maple. And he computed the following integrals. These are 0 to infinity, sine x over x, and 0 to infinity, sine x over x, sine x over 3 over x over 3. And we will see a pattern here. Nope. No, no, thank you. I see what you're saying. Yeah, missed putting signs in, not that I had put signs in. Yeah, no, it's sine of x over x, sine x over 3 over x over 3, sine x over 5 over x over 5, and integrated with respect to the x each time. And of course, we all know how to do this one because we've all taken complex analysis. We know the contour change to do, right? Right? So this is particularly beautiful, pi by 2. This is a little bit more complicated. Anyone know how to do this one? This one turns out to be pi by 2. Again, more complicated. This one turns out to be pi by 2. Now, mathematicians love patterns, right? Can we sense a pattern here?
Engineer's induction.
Engineer's induction, right. Any engineers here? Okay, you're satisfied. But this is being recorded, right?
Yeah.
We'll send it off to the Dean of Engineering.
Yeah.
So, dot, 20 sine x over x sine 3x over 3 over x over 3 line x over 13 over x over 13 is equal to, this time it's pi by 2. And Any guesses?
Not higher.
I over two.
Yeah. I should have actually done 11 here and then 13, but this is less than pi by 2.
No.
Very, very close to pi by 2. And this he found a little bit surprising and disconcerting. And once he recovered from his surprise and consternation, he figured out why it was. But he shot an email off to the people who maintain Maple. And very rapidly got a response from Mike Monaghan, who is a great guy. Oh, I don't know what's wrong. We'll have this bug fixed by the morning. And he let that sit for a little bit, and then he sent back a response, which is, no, actually, I just wanted to show you something that is actually a real thing. How would this be? There is actually a really good answer to why here. What's going on is that one way of doing this integral is to end up doing an integral in many dimensions of a region that basically looks like a hypercube with a potentially intersecting plane. And this plane is governed by the value of the sum of the reciprocals of the odd integers in question. So here, 1/1 plus 1/3 plus 1/5 dot 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 plus 1/15. And if that sum, this sort of odd harmonic part of the sum of the harmonic series, is less than 1, it does not intersect with the region. And so at 13, the sum of the odd harmonic numbers up to 13 is 43,024, compared with the numerator 45,045. If you add this plus 1/15, we get the same numerator, but we get a slightly bigger denominator, which is bigger than 1. So this is less than 1, and this is bigger than 1. So this does not intersect with the region, and so we don't have to get any correction factor. Here it does interact, and that means that we cut off this small part of the region, and so we no longer get pi by 2.
So, is it known what the limiting value is if you continue this process?
I don't know the answer to that off the top of my head. My suspicion is it's probably 0. Because the plane is going to move far enough down, but I don't know that for sure. And so Schmidt read Borwehn's paper on this and said, "Oh, this is lovely. Let's get ridiculously better." He said, "Well, for a while becomes for a bit longer." Oh, I'm sorry. This is for a long while.
I have a quick question.
Yes.
So we're excluding 1 from the sum, right?
Oh, yeah. Sorry. Yeah, otherwise it's ridiculous. Okay, so. Exact date. Yeah, then Peter Schmidt. Integral from 0 to infinity of 2 cos x sine x over x. X is pi by 2. Integral from 0 to infinity of 2 cos x sine x over x sine x over 3 over x over 3 is pi by 2. We went out to the product, the integral of the product of 2 cosine x times the sine x over x, sine x over 3 over x over 3, all the way up to sine x over 111 over x over 111. That is all equal to pi by 2. And then the same thing is less than pi by 2. So he was able to take this a long while further. And if you want to know more about this, there's a lovely blog by John Baez. Anybody aware of John Baez? Not aware of John Baez?
They gave a talk today.
He gave a talk today on illustrating mathematics. John is one of the more creative mathematical thinkers out there. He's a math physicist at UC Riverside.
Yeah.
Many years ago, when I was at Georgia Tech, we interviewed him and tried to persuade him to take a job at Georgia Tech, and he decided he liked California life better. His claim to fame outside of mathematics is he is the nephew of Joan Baez, the singer. You can argue whether she's a better singer or he's a better mathematician, but they're both incredible in their own fields. And he blogs extensively about mathematics and has a lovely blog on this topic. He takes a moving averages approach to intuitively understanding why such promising patterns break down at a certain point. Okay, so that was not pi for a long while. That was pi for a while. This is pi for a long while. So pi for a while was out to 111, out to 113, it broke down. So let's see an example where we can get maybe a little bit further out. As I said, we should find nothing surprising in numbers that are not equal to pi. Most numbers are not equal to pi. Here we have 1 over 10 to the 5 times the sum from n equals negative infinity to infinity of e to the minus n squared over 10 to the 10. Square the whole thing and we do not get pi. But it's correct to more than 40 decimal places. So let's look at why we might expect this to be close to pi. This is going off like a quadratic. This is a sum. This quadratic is going off moderately slowly, so its values look very close together. So this is well approximated by an integral. And this is a scaling factor. So this looks like the integral of e to the minus x squared with some sort of scaling going on. And we know how to integrate e to the minus x squared, and we see root pi is coming in, and oh, we've squared it, so we might expect this to be close to pi. I forgot a word, sorry. This is correct to more than 40 billion digits. And we can tell how far off it is. We can write down very, very accurately what the difference is between this squared and pi. And then we get a correction factor, which we can write down exactly. And if we take that correction factor, that gets us to within 80 billion digits. And we can write down the correction factor for the 80 billion digits exactly. And that will get us to 120 billion digits. So I was teaching a history of math class some number of years ago, probably an integer number of years ago, because it was on March 14th, some number of years ago. So that suggests it was an integer. In the honors college, I was doing a course on the history of math, and it was Pi Day. So let's talk about pi. And it was recent enough that I had an old Google 7 tablet, but I didn't have a Google phone. I don't think I had a smartphone at the time. So I can sort of place how far back it had to be, and I can get a lower bound on how recent it had to be, sorry, an upper bound on how recent it had to be, because it was in Crib Hall, and that's only been built for a few years. So I was teaching something that I'll show you in a few minutes, and I wanted to get a correct statement of it. And so I looked up in a book called the Pi Source Book, which is a wonderful, thick, heavy volume of information about pi. And I found the page which I wanted, and I scrolled up on this PDF file, and right above it was this. And I go, what the heck? Why is this? And it turns out there's a really good reason for this. And if you try and approximate this by an integral, and you write down, I don't know, the trapezoid rule, you'll get that this is a good approximation to pi. And you'll probably get 40 digits. You probably won't get 40 billion digits. So if you get something like this, it's usually a good idea to use smarter mathematics. And the math here is Jacobi theta functions. We define theta of t to be the sum of e to the minus pi n squared t. This is one particular value of a Jacobi theta function. There are much more general thing than this. Jacobi was a brilliant mathematician, and he showed something called the Jacobi triple product identity, which if you take a good course on generating functions, you might end up seeing. He did a huge amount of transformations of series, and he showed that the function theta of t satisfies the remarkable property that theta of t is the same as 1 over the square root of t times theta of 1 over t. And so now what you can do is take this and write down what you would need for that to be theta, for the function here to be theta of t, what t would be in terms of pi and 10 to the 10. And you can write it using the reciprocal. I'm going to leave this as an exercise. But what it does is it converts it to something like this instead. And now we have this huge number in the numerator, in the denominator, in the exponent. So the first term here, this is n greater than n equals minus infinity to infinity. So the middle term is 1. And we get a 1 over root, we get a root pi here. And you get a 10 to the 5 coming out. And then we square the whole dang thing. And the main term, the leading term is 1. And then the next term is something like e to the minus 10 to the 10 over pi. Twice. And the next term is 2 times e to the minus 10 to the 20 over pi. Sorry. 10 to the 10 times 4. This term is 1. Oh, sorry. This term is 1. Here we get something really tiny. Here we get something that's almost infinitesimal by comparison. And so we get to square it, and we get pi times 1 plus something really small on the order of 10 to the minus 40. And we can actually write down what it is and what the next term is and expand out the square and really get very good approximations to how far off this thing is from. So this really is for a very long while. Now, I want to write down a number. My last example, and I think I've just got enough time for this. Last example I want to give you is a number that is not pi in all the right places. All the right places. And it's actually not pi by 4. Pi by 4 is 1 minus 1/3. It's just the organization, isn't it? Yeah. Yeah. So-called Gregory theory, which was discovered by several people before Gregory discovered it, but he was British, so we celebrate that. Another instance of those who control the economy, control the naming of scientific results. So let's bring the 4 over. Gregory was sort of the adopter of new technologies of his day. He lived in Edinburgh, and when the grandfather clock was invented, he had one shipped up to his house in Scotland from London. It's like, you know, you go out, you buy the latest Apple Watch. Nowadays, he went and ordered the latest in timing technology from London. So, let's consider four times the sum, k equals 1 to 500,000. So let's truncate this. Minus 1 to the k minus 1 over 2k minus 1. So the series, but we're going to truncate it out to 500,000 terms. So this is the last term is about 1 over 100,000, so 1 over 10 to the 5. And so if you do the alternating series test, we see that we should get an error of size something like 10 to the minus 5. It should be about that over 2. So this gives 3.14159. So it's not 2. The glasses I can't read. And then the next digit was 6535. 8, 9, 7, 9, 3, 2. Four, 0. Four, 6, 2, 6, 4, 3, 3. Anybody know the digits of pi to more than 20 places?
3.32759.
So Matt, how are we doing?
4, 6, 2. What's that? I can't read it. 338, 327. What come after that? So what should come after that is 8327? Is that what you're at? It looks like we've underlined the wrong ones. Everything else looks right, I think.
6, 5, 3, 5.
535
8, 9, 7.
3. It should be 3, 2.
I think it's
9, 3, 2.
And then it's supposed to be a 3 after that.
Yeah, it should be 3, 2, 3.
Yeah.
8, 4, 6, 2, 6, 4, 3, 3.
Okay, I've mistranscribed it from in the
No, it's,
paper.
okay.
It is the case that the digits that are wrong are here, and here, and here, and here. So we get remarkable accuracy, except in the places where we don't. So R.D. North from Colorado, who was a mathematical gadfly, and in the early 80s had a computer. Idea how rare it was for people to have their own computer in the early 80s. Early adopter again. And he wrote a Pascal program to compute this. And he truncated it here. And he had enough sense to know that this is where we should be off by about 2 times 10 to the minus 5. So whatever we're supposed to be off by, we were. And he didn't expect the following, though. He didn't expect these digits to all be right and then these ones to be wrong. And these ones all to be right and then these ones to be wrong. And so, as any good crank does, he found out who were the top people in the field for computing pi. And at that point, it was before the Chudnovsky brothers had taken the baton from the Borwein brothers. The Borwein brothers had written a book called Pi and the AGM about how the arithmetic geometric mean converges to pi and how that enables us to use formulae by Manajan to get very fast algorithms for computing digits of pi, to make it possible to compute 1 million digits of pi, which prior to that had been unthinkable. Now, the Chudnovsky brothers took it further, and other people have taken it further still, and with hardware as well as software improvements, we've gone now to some large number of trillions of digits. I have not seen a new result today. Usually one comes out on Pi Day, somebody announces I can now get, this many trillion digits. So the Borwein brothers were really smart. And they paired up with Carl Dilcher. They were all at Dalhousie at the time. Dilcher, I think, retires next month. He either retired last year or next month. So he was early in his career back then. And they wrote a paper on why this happens. Now, some of you may have heard of Euler-Maclaurin summation, which expresses the relationship between smooth sums and integrals of smooth functions. And if you haven't seen Euler-Maclaurin summation, it is one of my favorite results in mathematics. It says that you can approximate a sum by an integral, and you can write down all sorts of interesting facts about the approximation. It gets you everything about Stirling's approximation. Excuse me, Stirling's approximation for log of n factorial, except for the log of the square root of 2 pi. You have to get that one by being clever. But Maclaurin gets you all of the other asymptotics, including constant over n squared, constant n over n cubed, constant over n to the 4, and so on. And the constants are all explicitly computable in terms of Bernoulli numbers. What Boolean and Dilcher did was they said, well, we've got an alternating sum here. How can we do something akin to Euler-Maclaurin, which is for non-alternating sums? How can we sum alternating sums? And it turned out that a little seeking around, and Dilcher had written a chapter in the handbook of special functions on Boolean summation, which is exactly what you need. And unlike Euler-Maclaurin summation, which needs Bernoulli numbers, Boolean summation needs Euler numbers. And so it turns out you can write things, you can write approximation to sums in terms of Euler numbers, and the Euler numbers appear as these differences, and the series that you get that predicts these is just using Boolean summation with Euler numbers instead of Euler summation with Bernoulli numbers. So it's Euler-Boole merely, as opposed to Euler-Bernoulli. So these are a few numbers that are strangely close to pi, with a few reasons why they are not actually pi. Sometimes they're pi for a while, sometimes they're pi for a very long while, sometimes they're pi in all but the right places. With that, I'll say thank you for your attention.
This last number, is that, can you prove that the proportion of digits of pi that are correct to the proportion of digits of pi that are incorrect are greater than 1/10? Or is it just that this follows a pattern for a while?
There's a good question there, which is how fast do the Euler numbers grow in that formula? And I don't know that off the top of my head. But a great question is go look at the original paper, which is in the monthly in 1989, I believe. It's a beautifully written paper, and investigate the growth rate of the Euler numbers, which is well known, just like the Bernoulli numbers, their growth rate is well known, and answer that question.
So I just looked, and the number in March of 2024 was about 105 trillion digits, and in July it was 202 trillion digits.
But it hasn't been updated
It
today.
hasn't been updated today.
So 202 trillion digits of pi. We know it's not rational. We know it's not algebraic. It's highly likely that if you encode every text ever written in ASCII, and you represent it in decimal as a decimal number, if you go out far enough in pi, you will find that decimal. It is widely believed that pi is normal in every base. That is, the digits have the right distribution in base 2. Ones and zeros appear with the right frequency. 0, 0, 0, 1, 1, 0, 1, 1 appear with the right frequency, and so on. It's believed to be normal in base 10, so every k digit number appears about 10 to the minus k of the time as you look out across many, many digits. And experimentally, this has been verified for shortish lengths going out as far as we've been able to compute. But it's a problem that appears to be beyond hope of proof right now.
Isn't there something close to a closed formula, closed form formula finding the nth digit of pi in hexadecimal?
In hexadecimal digit, there is an algorithm which will also give you the nth bit. It's how I like to think of it. It's so-called Bailey, Borwein, and Plouffe algorithm. Plouffe is a very clever but very strange and reclusive fellow who was working at the time at Simon Fraser with Peter Borwein and David Bailey came into the picture, and they found this amazing expression that allowed them to write an expression for the kth bit, which could be computed without computing all of the previous k bits first. So it gives you a way of just asking for some bits out here. Yeah.
That's cool.
And BDP is the search term of art for that. And no, there is not one that is known for base 10. And the identity that they found that gives this for base 2 or base 16, that identity, that equivalent form of identity has been searched for and is known, I believe, is known not to exist for base 10. So it's likely that there will not be an algorithm unless somebody else very clever comes along and does something very different. That we will probably not be able to do the same thing in base 10. Or most other bases. And there was some hope that that might allow us to show that pi is normal to base 2. That has not panned out. I last talked to David Bailey about that about almost 10 years ago, and he said he had no substantial hope that it was going to pan out.
So things might have been different if we had 8 fingers.
Yes, we do. Things might be different if we didn't use our thumbs.
Right. Other questions? All right, let's thank Neil again. We'll do more after spring break. I hope everybody has a relaxing and fun spring break. Be careful, and we'll see you on Monday after.
And there are a few copies of this paper, if anyone wants to take them. One of them is not sampled, you know.
All pizza, no pizza left behind. Mono of the math club.
Yeah, that's what they're talking
This
about.
one is today, and
What?
bring out.
What good